So before I start, thank you very much to the organizers. I've already thanked Richard, but everybody else, I've had a wonderful few days. Great talks. So today we'll talk a little bit about something that hasn't been discussed a whole lot, which is databases that are used in forensics. And I'm going to talk about, I think, talk mostly about databases used in casework, but I will talk a little bit about databases used in research. I have collaborators in this work. This is a project that is being led. Well, first of all, let me tell you about CSAFE. This is the Center for Statistics and Applications in Forensic Evidence, and we were established about a year ago with funding from NIST, the National Institute of Standards and Technology in the United States, and we are a consortium of 4 universities. University of California, Irvine, there's our representative. University of Virginia, there's our representative. Carnegie Mellon University, and Steve Fienberg is a PI for Carnegie Mellon, and myself. And we are embarking on a bunch of different projects, and if anybody would like to work with us or visit or spend time, we're delighted to have you. So Anjali Mazumder, whom I'm thinking that many of you know, is the lead on this project. Steve, Bill Eddy from Carnegie Mellon, Hal Stern from UCI, and myself are also working on it. So here's an outline for what I want to discuss today. So I'll talk a little bit about uses of databases in forensic science, talk about the characteristics, first of all, desirable characteristics that databases ought to have and for what purpose, and then the characteristics of some of the forensic databases with which I'm familiar. There's a lot of convenience samples out there. I'll talk a little bit about limitations of convenience samples from a statistical point of view, and propose some things that may be doable in order to improve some of the databases that are out there. So there's a bazillion uses of data in forensic sciences, but I'll talk about 3. One of them, of course, is the use for development of new methods, right? So if you want to develop a new analytical method, you have to have some data on which you're going to be basing your research. Once you have developed a method, you have to have proof of concept. Does the method work? And what do we mean by work? And finally, there's a lot of use in what we would call casework. And casework here, I put it in parentheses because it may include a lot of different things. It may include identifying, find something on a crime scene and you want to identify what type of object this might be. For example, you find a shoe print, you may go to some database to decide what model, what make, what everything else that shoe might be. You want to identify sometimes the source of an object. So I have some spent cartridges at a crime scene, and I want to know whether there's some gun that may have been used in a different crime that's on some database. And finally, I might want to estimate population frequencies, for example, allelic frequencies at a given locus on some subpopulation. So for all these purposes, we're going to be using some kind of a database. And the question is, what attributes ought to be present in those databases? So we can think of a lot of attributes, and I don't pretend for this to be an exhaustive list, but of course we can think of the size of a data set, and of course small data sets, even if they're very wonderfully well collected, random, and following all the nice approaches in sampling, if they're very small, they will result in estimates of whatever quantities you're obtaining from those data that are pretty uncertain, right? So that have a lot of sampling error. Completeness, what do we mean by completeness? If you're a database person, if you're a computer science person, there's a very well-defined definition of completeness. It says that all true information about some item is contained in the database. From a statistical point of view, we talk about completeness in the sense that if there is heterogeneity in the population in terms of the attribute on which you're interested, this heterogeneity is well represented in the database. And of course, that before you can determine whether a data set is complete, you have to know a whole lot of things about the population from which you're drawing those data. Validity is, in the database world, the opposite of completeness. Well, not the opposite, the complement, if you will. All incorrect information about some item is excluded from the database. That's a little tough. That's a little difficult. Representativeness means that population subgroups are represented in the correct frequency in the population, in the sample, I mean. And so, again, you have to understand the population structure in order to decide whether your data set is representative or not. So I'll talk more about this in a little bit. And finally, if you're a statistician, knowing what the inclusion probability of each item in your data set might have been is really, really important. If you do not know, if you have no way of estimating what we would call inclusion probabilities, it's pretty impossible to make inferences about the population from which this data were drawn. And so that's a really important concept, but it's, again, a very difficult, it's a pretty high goalpost. It's hard to meet in order to know what the inclusion probability of each item in the sample was. You need to have what we call a complete sampling frame. In other words, you need to be able to enumerate your population in some way. Now, this seems like an impossible list of attributes to meet in each case, but the good thing is that not every attribute needs to be present for a database to be useful, at least for some purposes. So start with what I think is the easiest or the lowest bar, which is constructing a database that's useful for research purposes. Well, in this case, let's suppose that you want to develop some algorithm to extract some features from shoe prints. I don't know what features, some features from shoe prints. What do you really need? Well, you need a collection of shoe print images, right, that you can use to develop your methods. And you want a collection that's diverse so that you have many different patterns. So there's an issue of size. You cannot work with 2 or 3 shoe prints because you're not going to be having a diverse enough sample to work with. But you don't really need for that database to be complete, to be representative, or you could care less about probability of inclusion of each of the prints in your database. You just need a nice sample of sort of, you know, a good sample of images that will allow you to develop your algorithms. And that's, I'm not going to say much more about research databases. There's a bunch of research databases out there. I will talk a little bit more about them later. Of course, you know, you have to have included in your research databases the features that will allow you to estimate the parameters of plausible models that you want to apply to fit, right? And so I'll say something about that in a minute. The other use of data is for testing the method. So you now have developed your wonderful method. Now you have to show that it works. And here, what do we mean by work? Well, we may mean different things depending on on what we're working on. We might say the method is reliable, it is accurate, it has high sensitivity, it has high specificity, it has positive predictive value. There's any number of performance criteria that you can use to determine whether your method is working well. I love these pictures. So here you have a method that's both accurate and precise. Here you have accuracy but no precision. Here you have a lot of precision but no accuracy. This is a terrible case, I guess. And here you have neither accuracy nor precision. I think I'd rather be here than here. And so this is the type of stuff that you want to be able to test your new method for. And so what type of attributes do you require in your data set, in your validation, if you will, data set? Well, you have to have size and completeness. And in addition, you have to have ground truth information, if you will. So I need to know, for example, whether my method is correctly identifying a mate, let's say, suppose that I have shoe prints, or suppose that I have, stria and bullets, I need to know whether my method is declaring that these two things are similar when they truly are. And in fact, I needed to do this reliably and repeatedly, right? And so, again, representativeness and inclusion probabilities are not really necessary. It's nice if you have them, but it's not necessary to have them in order to test the validity of your method. So what are some basic principles that we need to think about when we're thinking about constructing a data set? So how do I start thinking about constructing a good data set for research or validation? Well, there's a few things that I absolutely have to know, right? I have to know something about the population of interest. If I'm working with shoe prints, I need to know something about the population of shoes. I need to know what features characterize the items in the population. If I'm working with glass, for example, maybe color, I'm going to say silly things, right? So if I'm working with glass, maybe refractive index is not that important, but elemental composition, the concentration of certain elements in glass is what I really want to focus on, because that's the most discriminating feature. I need to know something about those features behave in the population. For example, if I'm looking at 10 elements in glass, are those elements correlated? Or, if I observe a high level of aluminum, am I also going to observe a high level of calcium, to say something? Because that's going to determine the type of models I'm going to be fitting to those data, and therefore the type of data I am going to be needing to fit those models. And so I have to know something. Are those values associated? So what are the sources of variability in those features that I'm interested in? So for example, if I am looking at elemental composition in glass samples again, is the elemental composition associated with the type of glass? If I'm looking at bottles versus windshields versus window panes, the glass manufacturer, can I tell one manufacturer from the other if I am looking at elemental concentrations? Is there a variability within manufacturers? So if I look at glass manufactured by X today, is that different from the glass they manufacture 3 weeks from now? And so those are the things that I need to know before I can construct a data set that for example, is heterogeneous enough, represents the heterogeneity in my population. And so, for example, if I know that I'm looking at 10 elements in glass, and I know that in order to discriminate between different sources of glass, I need to look at the 10 elements. And let's suppose that I know that these 10 elemental concentrations are correlated. Then this tells me that on each sample of glass, I am going to have at least 11 fragments measured, because I'm going to have to compute or estimate a 10 by 10 covariance matrix, right? And so I need to have the degrees of freedom in statistical parlance to get at least a minimally acceptable estimate of that covariance matrix. And so if I have a bunch of glass samples, and on each glass I measure 3 fragments, I'm toast. There is nothing I can do in order to estimate a 10 by 10 covariance sample. It just doesn't happen. And so the data are going to be useful only if they permit estimation of parameters in plausible models. So again, I'll continue with glass as an example, because this is one of the few, so this is my pet peeve. In general, forensic databases are not accessible. So either they belong to governmental organizations, or like the FBI, they're not very nice about sharing their data, or they belong to researchers that won't share the data either. And so that's another big issue. But in an act of Glasnost, this was his own words, Peter Weiss from the Bundeskriminalamt sent me some glass data last year, as a matter of fact. So these are and he didn't send me some crappy glass data. He sent me the glass data that they use to develop their methods. And these are the data that were used to develop a match criterion, which is considered at the moment the state of the art. This is what GLASS, a forensic scientist, after many years of work, find is the best matching criterion, let's call it. After much bitching and moaning, to pardon my French, we got another data set released. This was collected by Jose Almiral and his colleagues at the Florida International University. But I'll just talk about Peter's data because the structure of both databases is pretty similar. So here's what Peter's data, the BKA data looks like. So the data that I got has 63 different window panes. On 62 of them, there's one fragment measured on each one of the 62 window panes. The fragment is measured 6 times. Each fragment has 6 replicate measurements. And then there's one pane on which there were 34 fragments measured. And and one particular fragment that was measured 66 times. And so it's an interesting structure, as you can see. And so if you're a statistician, what do you do with data like this? So, so there's, if you're a statistician, the first thing you think about is a very simple analysis of variance model, where you say that, and this is a very simple model, where you say that if you look at the ith, I'm going to call them windows. If you look at the ith window, jth fragment, kth measurement in the fragment, you could say that there's an effective window, there's an effective fragment within window, and then there's the measurement error or observation error for the physical scientist in you. And so we can think of a between windows variance in elemental concentrations, a within window between fragment variability, and a between measurement within fragment variability. This tends to be very, very, very small because this has to do with the precision with which you can measure elemental concentrations. And in fact, indeed, it is truly tiny in glass. And so there's a variance structure. So if I look at the variance of any old fragment, somebody gives me a fragment and says, what's the variance of this fragment in terms of elemental concentrations? Well, this is 3 components, right? The between window, the within window, and the measurement error variability. If I look at the covariance between two measurements of the same fragment in the same window, then there's a covariance. These things are correlated because they come from the same window. And if I look at the average measurement of 2 fragments from 2 different windows, from the same window, then there's a source of covariance there. And finally, 2 fragments from 2 windows can be assumed to be uncorrelated. And so we had data on 18 elemental concentrations here. And so the only thing that I'm showing you, I just picked the first 7 by 7 block of the correlation matrix. This is the correlation matrix computed on the log concentrations. And so this is just a piece of that correlation matrix. And the only reason I'm showing you this piece is to show you that, in fact, some of these correlations are pretty darn large. 0.74, 0.77, 0.88, 0.94, 0.96, 0.88. So you really cannot ignore them, right? So these are pretty large correlations. And if you're going to be doing an analysis on elemental concentrations of glass, you should really have the data that you need in order to estimate those correlations. By the way, these correlations, how did I estimate them? I estimated them using the one window for which we had 34 fragments. Now, that's an estimate. Would I use that estimate in casework from one window? Never. And so, I have a sample of 1. The only thing that this is telling me is that I better get more data. because I have to be able to estimate these correlations. And so these data really do not support a plausible analysis. The state-of-the-art approach, what is currently advocated by the GLASS examiners, the best that they can do at this moment, is carried out element-wise. So one element at a time, ignoring the fact that these elements are correlated. And so that assumption of no correlation among elements is really not a correct assumption. It's easily provably shown to be wrong. And so the problem is that there are no data sets out there. I don't know what the Dutch data set looks like. The F&I people have data, but I don't know what those data look like. But in the United States, there are no data sets that will allow estimation of these within sample covariance matrices. And so what we're doing at this moment is just, and I'm talking to, I had a long conversation with somebody from the FBI who's spending about $500,000 collecting new GLASS data with 2 measurements per window or per sample. And I'm telling her, I say, you cannot do this. Well, she goes, why shouldn't I do that? This is, we're trying to mimic what we get in casework. You know, that's not a good model for data collection. Anyway, and so what we're doing now is we're in the process of carrying out a very large simulation study with a PhD student of mine, just to show the consequences, you know, trying to mimic what GLASS data look like, and just to show the effect of ignoring correlations on the sensitivity and specificity of, you know, the proposed approach by the GLASS expert, and an alternative approach that we've been working on that is very simple and based on distances between pairs of known matches and known non-matches. And I have to bring up, I have to bring up this comment here. Many years ago, Hal Stern, Mike Daniels, Mike Daniels and myself worked on bullet-lead. This was probably the first bullet-lead analysis, or one of the earliest bullet-lead analysis for the FBI. And I have to say that the bullet-lead problem and the GLASS elemental composition problem are absolutely identical from a statistical point of view. And many of the issues that arose at the time on bullet-lead that we have obviously all forgotten about are now being repeated exactly the same way in the analysis of GLASS. Anyway, casework. Oh my, I'm out of time.
5 minutes.
5 minutes, okay. So I have to hurry a lot. So data used in casework, I'm going to be talking mostly about the issue of estimating let's suppose that you're doing some sort of likelihood ratio approach. And you know, in order to estimate the denominator of the likelihood ratio, you first have to formulate what you mean by the defense hypothesis. But once you have formulated that, there's no getting around the fact that you're going to need some population information in order to estimate that denominator in a likelihood ratio. So what do we need in order to compute the denominator in a likelihood ratio? Well, now the issue of representativeness of your database turns out to be extraordinarily important. So most of the databases that have been assembled, and I am not going to be talking about DNA databases because I don't know enough about those, but I'll talk about all the other databases. Most of the ones that have been assembled are really samples of convenience. So these are databases that include items collected from crime scenes or from criminals or from some other sources, but certainly are not the result of some systematic, well-designed random approach. And so so the question is, and this is another discussion I have had with some scientists about shoes in particular. The issue is, do we really need a representative sample of shoes, or can we use these convenience samples if I want to compute the denominator of a likelihood ratio? So here's a very simple example. So there's a crime committed and a shoe print is found at the scene, and I have a neighbor that hates me, And so she tells the police that she saw me lurking around the crime scene. And I happen to have a shoe that I purchased in Uruguay, let's say, and that matches the crime scene print. And so the police search the shoe print database. They have 5,000 prints of shoes that were obtained in a convenient way, and find that my shoe appears only one in the 5,000 pairs of shoes. And so the frequency of my shoe is like 1 in 5,000. I'm toast. I'm marched straight off to jail because, of course, the likelihood ratio is 5,000. So what's wrong with that picture? Well, what's wrong with this picture is that I have, if that is the reference population, that's not necessarily the reference population that I belong to. I am an innocent person. I was not the criminal in this case. And so let's suppose that where I live, the true frequency of shoes like mine is 1 in 100, not 1 in 5,000. The fact that criminals don't use the type of shoe that I use makes a difference here. And so convenience samples will always, no matter what you say, always result in biased estimates of population frequencies and other quantities. Come hell or high water, there is a bias there. And so if even if the suspect happens to be a criminal, and that was the right denominator, there's still a bias in the population frequencies that have been estimated. And if you're not the criminal, and if the attribute, for example, shoe type, is not distributed uniformly across population subgroups, then you're truly toast. So to construct a database that can be used to estimate population frequencies and the probative value of evidence, one has to consider two approaches, and none of them are easy. One of them is to use principles of sampling theory. There's a whole field out there to construct a probability sample where we know the probability of selection of each unit in the sample. Another one is attempt to correct existing databases to try and remove those biases that are unavoidable with databases that are non-representative. And there's many ways to do this. One way is something called post-stratification. And so both approaches are expensive and require a whole lot more information than what we have. I have 2 slides. 2 slides? Very quickly. So in any event, you have to know your population. You have to understand all the sources of variability. You have to have an estimate of the frequency of each stratum in a population. You have to have an idea of the heterogeneity of the attribute in a population. And you have to have, ideally, a sampling frame, which you never have, but let's suppose that you do. You have to be able to design a sample. Simple random sampling is easy, but typically very inefficient. You have to decide on a sample size. And finally, you have to be able to construct weights, and this is where it comes in. So the last slide, next to last slide, let's suppose that in the state of Iowa there's 1 million firearms, and I'm not exaggerating. Of these, half are Glocks, another 25% are Beretta, and the remaining 25% are Colt. And the police have assembled a non-random database of 1,000 firearms, where 80% are Berettas and 10% are Glocks and the other 10% are Colts. And so how do I do post-stratification in this database? Well, obviously I have too few Glocks in my sample and too many Berettas, so I have to upweigh the Glocks and downweigh the Berettas. And so to correct the sample frequencies, all I have to do is look at the population frequencies and divide them by the sample frequencies to get this post-stratification weight. It's a very simple process. The only problem is that I have to know the population frequencies, which is where the issue starts. So unfortunately, most databases are lacking in some important aspects, and the reference databases that we use for calculate probative values must be representative, perhaps after weighting. And this doesn't say, it's not an easy thing. Manufactured items change from year to year, and so you have to continuously update these databases, and thank you. Sorry.
I have the right to ask my questions, I'm the chairperson. Very quickly, have you encountered a case where the skewed information from the database because it's a criminal population actually made a difference in the court?
Well, no, and it's very hard to know. You know, this is. Huh?
Yeah, well, an American case.
No.
Okay, Rick, let's.
Sorry.